Hi, in this short video we're going to describe the fill-in process in direct methods. To do so, consider the following example: matrix A where all non-zero entries are concentrated in the main diagonal, first column and first row. Now, if we perform an LU crowd factorization of this matrix, we see how entries that were originally 0 in matrix A become non-zero in L and U. This, of course, has a negative impact in the computational cost because we need to first compute, second store these fill-in entries, these new non-zero entries, and then take them into account in the two substitutions, in the forward substitution with matrix L and the backward substitution with matrix U. Okay. This fill-in process has some rules. We can see here in the second example, for instance, how the column profile, also called skyline, of the upper triangle of matrix A is respected by U, and how the row profile of the lower triangle of matrix A is respected by L. We are discussing here for a factorization method, but exactly the same fill-in process is observed with Gaussian elimination. In some cases, fill-in may have a modest computational impact. Consider, for instance, this two-dimensional structure where all non-zero entries of the stiffness matrix are concentrated in a narrow band along the main diagonal. Okay. Then, in this case, fill-in is very modest. We need to zoom in to note how, for instance, this 0 becomes a non-zero here, but in any case, very small fill-in. The situation is different from a three-dimensional structure or a three-dimensional finite element mesh. Consider, for instance, this case where the stiffness matrix has a much wider band. We can see here that fill-in is important, especially in this zone, always respected the bandwidth of the matrix. Okay. Imagine now the following scenario. Instead of having the natural ordering of the nodes of the structure, we have a random numbering. Okay. In other words, imagine that the stiffness matrix, instead of having this banded structure, has this random structure. Okay. Of course, the number of non-zero entries in matrix A is exactly the same because we are not changing the connectivity between nodes, we are only changing the node numbering, but the effect on fill-in changes a lot. We go from this number of non-zero entries to this number of non-zero entries, okay, with a much wider zone of fill-in. For finer and finer meshes, the situation may get worse. So this is the case with the natural ordering of the nodes, where we get this fill-in. If we go to a random numbering, then fill-in is much more important. That is to say, fill-in depends not only on the number of non-zero entries of matrix A, but also on how are they located. Okay? For this reason, renumbering techniques may be used to reduce fill-in. Okay? Consider, for instance, the following example: a matrix A like this. If we apply directly a factorization method, we can obtain a situation matrix L transpose like this, with all this fill-in, it may be convenient to renumber the nodes of the finite element mesh, that is to say, to change in the same manner columns and rows. In this way, we get a much narrower band, and then fill-in is considerably reduced. Okay? There are many such renumbering strategies. MATLAB, for instance, has the so-called reverse Cahill-McKee ordering embedded in command sim RCM.